Okay, hello and welcome everyone. In this video, I'm going to do a walkthrough of 4 exercises that are relevant for consumer theory. So utility maximization type questions. So we'll start off. Jack has the quasi-log linear utility function. Utilities coming from good 1 and good 2 is going to be the sum of the amount of good 1 and 4 times the natural log of good 2, or the consumption of good 2. Jack's income is $240, faces prices of $40 each. We got to find the margin rate of substitution. We got to find Jack's optimal bundle. Suppose Jack's income falls from 240 to 80. What happens to the optimal bundle? If Jack's income was 80, but somebody gives him another $40, what's Jack going to do? But if somebody then matches his income and gives him another $80, so now Jack has 160. All right, so we want to find the optimal bundles under all those circumstances. The first thing, we have to find the margin rate of substitution. That's going to be the ratio of marginal utilities, MU1 divided by MU2. So I've got this right here. That's the partial of this utility function with respect to 1. That's what this notation is doing. This is the partial of the utility function with respect to argument 1. Okay, that derivative here is just going to be 1. What about my partial with respect to good 2? Well, remember the derivative of the natural log of x is just 1 over x. So that 4 times 1 over q2. All right, we draw a division bar here. We have our ratio, and that'll give us our margin rate of substitution. So 1 divided by 4 over q2 is going to be, what, 1/4 q2. All right, so that is our marginal rate of substitution. We'll set that equal to the marginal rate of transformation, the MRT. That's just another name for the price ratio. In this case, that's 40 over 40, or just 1. And so a quarter Q2 is equal to 1, or Q2 is equal to 4, is Jack's demand, Jack's optimal amount, optimal consumption of good 2. This indeed is a Marshallian demand. This is going to be demand. It's going to be written ultimately as a function of the price of both goods and the income. That's buried in this number. Hard to see with a numerical value, obviously. Anyway, this is Jack's demand for good 2. Now we have to find Jack's demand for good 1. So let's go to the budget constraint. 40Q1 plus 40Q2 is equal to 240. Why? These 40s are the prices. This is the expenditure on good 2, which must match exactly the income available. Okay, so 40Q1 plus 160. Why? Because 40 times 4 equals 240, or 40Q1 is equal to 80. 40Q1 is equal to 80 divided by 2. I lost my 2 here, right? Shoot. Anyway, not 2. This should be, what am I saying? This is supposed to be 40. This is supposed to be 80 divided by 40. Yeah, so I lost. This should be Q1 is equal to 80 over 40 is equal to Q1 over 2. Matter of fact, this is bothering me so much. I might be able to fix it. Let me try to be a little bit clever here. This time I'm going to use a text box. So I'm going to say this is going to be divided by 40. Is that better? I don't know. I think it's better. Anyway, so that's what that should do there. Good, we fixed it. All right, with Jack's remaining income, Jack is going to purchase these 2 units of good 1. Right, so Jack's optimal amounts of good 1 and good 2 is going to be 2 units of good 1, 4 units of good 2. All right, suppose now Jack's income is only $80. What's Jack going to do? Well, remember, one of these, Jack is going to be hyper vigilant about. Whatever is going to drop out immediately from comparing MRS to MRT is this Q2 is equal to 4. So Jack is really keyed in on good 2, and so Jack is going to try to continue to consume good 2. Well, with $80 available and costing $40 each, Jack's only going to be able to afford 2 units of good 2. Sorry, I should be pointing down here. Jack can no longer afford 4 units of good 2, so Jack is going to choose 2 units of good 2 and then not buy any of good 1. This is a corner solution, and the MRS is not equal to MRT, right? What's happening here? Well, if we're comparing the margin rate of substitution, Q2 over 4 is equal to the price ratio, 40 over 40 is 1. Clearly, at the optimal bundle that Jack's getting, this is 2, so this is going to be 2/4. This is 1/2 is less than 1. So the MRS is less than the price ratio. Wait, that's our alley solution. Remember our econ friends, Alex and Allie? This is our alley, our all Y solution. The solution is going to be on the vertical axis. This is a corner solution. Jack is going to spend all of his money on good Y. In this case, it's good 2. If you put good 2 on the vertical axis and good 1 on the horizontal axis. And so this is a situation where, though the MRS is not going to be equal to the price ratio, Jack is going to be optimizing by continually buying more of good Y. Now, it's interesting because it's not truly the situation where Jack wants to purchase only Y, because at a certain point, Jack's going to switch over and start buying good 1, as we saw from above. But this intuition's helpful, getting us in the right direction. What this is a reference from, if you haven't seen the other videos or if don't remember, is this is referencing the solution with perfect substitutes. So I've got some videos and problems on those as well. All right, so what about Ann? So Ann's preference structure, oh, sorry, here I'm getting ahead of myself. So we have to determine what happens to Jack if he actually gets more money. So Jack's income was still $80. What will Jack do if somebody gives him another $40 from this situation where Jack's currently buying 2 units, right? 2 units of good 2. What's Jack going to do if he gets another $40? Well, he really wants, he's keyed in on getting 4 units of good 2. So Jack's just going to buy another unit. He's going to buy that 3rd unit of good 2 that he is missing. So now Q2 is going to be equal to 3. Good 1 still is going to be no expenditure on good 1. All right, lastly, if Jack has $160, right? Somebody doubled, matched how much he had. Now Jack can afford this original bundle, and that's exactly what he's going to do. Jack's going to buy 4 units of good 2. Still not able to afford any good 1 beyond his allotment of good 2. What happens if we give Jack another $40? Jack will keep buying 4 units here, and we'll go and buy 1 unit of good 1. After Jack's gotten 4 units of good 2, Jack will start buying good 1. All right, so what about Ann? Ann's preferences are Cobb Douglas, right? X to the 1/4, Y to the 3/4. Budget constraint is going to be 2x plus 3y is equal to 24. You might recognize our generic Cobb Douglas demands buried in here, right? So our Cobb Douglas demands for good X is going to be what? Alpha over alpha plus beta, m over px. So that's going to be 1/4 m over px. And then beta over alpha plus beta, m over py. So it'll be 3/4 m over py. But let's solve for it. So let's write down Ann's consumer maximization problem, get the MRS, and find Ann's optimal bundle. Are these good substitutes or complements for Ann? Well, we know with Cobb Douglas, these are going to be neither substitutes nor complements, because the demands are going to depend only on income and the goods own price. But we'll see that when we see the demands. Suppose the price of good X increases by a factor of 10. Find Y. Find the optimal amount of Y. This is key for your understanding of how Cobb Douglas demands work, right? I really like this question. And then what proportion of income does Ann spend on good X and good Y? This is that property, that cool property about Cobb Douglas. It appears at the end of my choice examples video. So anyway, so we have to solve for Ann's. We have to set up and solve Ann's consumer maximization problem. Find the MRS. I didn't write out the maximization problem in the solution. That was really bad. So what's the maximization problem? It's going to be maximize utility. This is the objective function, maximize utility by choosing X and Y subject to this budget constraint. And then you could write out the Lagrangian. The Lagrangian would be, so L, oh, this is going to be a disaster. So here I'm regretting doing this immediately. I wonder if the text box will be less of a disaster. So this will be L is going to be, let's see, well, let's do it this way. UXY minus lambda times budget constraint. So this is what we would want, and then we'll take our partials and then solve for a system of partial equations. So partial derivatives. So the utility function in a Lagrangian, you replace that with this, x to the 1/4, y to the 3/4, minus lambda. You probably just actually write that as like, looks like the upside down y, times the BC. What's that? The budget constraint. This right here. It's going to be m minus, so 24 minus 2x minus 3y, right? And then that'll give us the form. Alternatively, you could just take the partial derivatives with respect of the utility function with respect to x and with respect to y. Take their ratio, that's the marginal rate of substitution, and then set that equal to the price ratio. We know the price ratio, that's just the slope of the budget constraint. That's going to be px over py. Price of good x is 2, price of good y is 3, so our price ratio is 2/3. All right. Anyway, but let me walk through these derivatives, the derivatives from our marginal utilities. I can't see this, I guess. Maybe I move this a little bit, you can see. Okay, I'll try to put these, it's not gonna let me put them both on the same, I didn't make my screen big enough, sorry. Anyway, so let me just walk through the derivative here, and then we'll see it down below. So the derivative here, the partial, is gonna be 1/4, bring that out front, reduce this power by 1, so it's gonna be 1/4 x to the minus 3/4, y to the 3/4 comes along for the ride. That's our partial with respect to good x. Our partial with respect to partial with respect to good x, that's this. Partial with respect to good y, where's this coming from? Well, it's going to be 3/4, bring that out front. X to the 1/4 comes along for the ride. Y to the 3/4 minus 1. So y to the minus 1/4. That's this right here. If you divide one by the other, this divided by that implies our marginal rate of substitution is going to be y over 3x. With Cobb Douglas, right? Cobb Douglas, the marginal rate of substitution is always going to be your y over x and then some constants, right? Or x2 over x1 and some constants. So I'm always going to get y over x and then whatever are the constants. So the 4's cancel, I'm left with that 3. That's what that's from. Set that equal to our price ratio, which is 2/3, and that boils down to our tangency condition, which is going to be 2x is equal to y. Substitute that into the budget constraint. I've done that here. If 2x is equal to y, I'm going to replace this 2x with a y. That's going to be 4y equals 24, or y is equal to 6. If y is equal to 6, then 2x plus 18 is 24, solves for 3 units of good x. So that's going to be Ann's optimal bundle. That's where we got this from. All right. Are these substitutes or complements? Neither, because both demands depend only on income and own price, right? These are our general Cobb Douglas demands for good x and for good y. It doesn't depend on the other good. It's price, right? So we can't observe substitutability or complementarity. Although there's something else we could say, but we won't worry about that here. Okay, so then part C. If the price of x increases by a factor of 10, find y star. I love this question because you're like, wait a second, price of good x increases by a factor of 10. How do we solve this? Well, we're trying to find the optimal y, but we have a function for that. So you realize, oh, let's look at the demand. You're like, wait a second, this doesn't have px in it. So obviously there's no change on y in response to that price change of x, right? So the optimal y is still just y star is equal to 6. All right, the next thing we want to determine is what proportion of income does Ann spend on good x and good y. Remember, with Cobb Douglas, each consumer is going to expend a constant share of their income on both goods. So my expenditure on good x is xpx. My expenditure on good y is ypy. My expenditure on good x is going to be 1/4 m. My expenditure on good y is going to be 3/4 m. Notice this. This is just from this right here. This is a constant. This boils down to 1/4. Why? Because this is what? 1/4 over 1/4 plus 3/4. So that's 1/4 times m over px. Let's move this px to the other side so I can write expenditure or share of an income as the expenditure as a share of income. Same thing over here. This is 3/4 divided by 1, or 3/4 times m over py. Let's move the py over here. This will be my expenditure on good y is equal to 3/4 of my income. That's cool. All right, so now suppose Emily's utility depends on the amount of time playing on the internet, time on video games. Emily's utility function is this right here, Cobb Douglas with this constant. Emily has 15 hours of free time to spend on these two activities each week, and the goal is to maximize utility. Set up the Lagrangian for the constrained maximization problem, find the necessary conditions, and then find the optimal amount of time spent surfing internet and playing games. Okay, so here's the Lagrangian. This is going to be the objective function, utility, and then here's the constraint, right? So this is the budget constraint, 15 hours. Each hour spent on each activity cost me 1 hour out of my budget, right? The prices have to be 1 here, because each hour that I spend is 1 hour from the 15 each hour I spend on video games is 1 fewer hour out of 15 that I can spend on the internet, for instance. The optimality conditions just take the partial with respect to x, partial with respect to y. Here's the partial with respect to x, partial with respect to y. This is the MRS right here. If you divide this by that, this is the price ratio. If you look at the coefficients on the lambdas, right? Lambda times 1 for each of those partials. So simplifying down, remember, this is Cobb Douglas. So with Cobb Douglas, right, I'm always going to have y over x and then the constants. Sure enough, that's what I have here. So I have 4y is equal to x. If 4y is equal to x, that's really easy to substitute into my budget constraint. 4x plus y is 15, or 4y is equal to x. So 4y plus y is equal to 15, y is equal to 3. If y is 3, x has to be 12. All right, so we have Emily's optimal consumption of internet and video games. What a day. All right. So consider three consumers, Jack, Owen, and Elodie. All three face the same prices for the both goods. Price of good X is 2, price of good Y is 1. They have the same income, 60. Given the following utility functions, find the optimal choice for the three characters. Will these three consumers ever purchase the same amounts? And assuming Jack can raise his income without Owen's rising, how much must Jack's income be in order to purchase the same amount purchased by Owen? Oh, this is just like the constant share of income thing. This is like because Jack has Cobb Douglas utility. You're like, wait a second, that doesn't look like Cobb Douglas utility. No, it is. This is Cobb Douglas utility. This right here is the natural log transform of Cobb Douglas utility, where the utility is just x times y. Right? Take the natural log of x times y, ln x plus ln y. Right? Okay, so find the optimal choice for all three characters. For Jack, well, we have to find Jack's margin rate of substitution. This is really easy. Partial with respect to x is 1 over x. Partial with respect to y is 1 over y. Sure enough, with Cobb Douglas, we're going to have y over x with our constants, but our constants were just 1. So there's our MRS, set that equal to our price ratio. That's what this is doing. Price of good x was 2, price of good y was 1, so 2x is equal to y. Plug that into our budget constraint. 2x plus 2x is 4x is equal to 60, so x is 15, and then y is 30. What about for Owen? Owen has perfect subs utility, with the slope of the indifference curves are 1 because the marginal utility of x is 5, marginal utility of y is 5. So mux over muy is 5 over 5 is 1. MRS is 1. Price ratio is 2, px over py. So the budget constraint is steeper than the indifference curves, which is our alley solution, all y. Right? So Owen is going to exhaust the budget on y. Y costs $1. Has 60 available, so Owen's going to buy 60 units of y. What about Elodie? This is going to be perfect complements. Let's replace this comma with an equal sign. So y is equal to x is our line, our ray through the origin that goes through the corners of these right angle indifference curves. Then let's substitute y equals x into the budget constraint. 2x plus x is equal to 60 is the budget constraint. So 2x plus y equals 60, or 2x plus x equals 60. Oh, x has to be equal to 20. If x is 20, then y is 20. Okay. For them all to purchase the same amount, they would need the prices of the two goods to be the same. If px is equal to py, both Owen, Cobb Douglas, and Elodie must purchase a bundle where x equals y to exhaust their budgets. The difficulty is Jack, who would optimize by purchasing any bundle along the budget constraint. Remember, there's three things that can happen with perfect subs, right? Jack's indifference curve have a slope of 1. This budget constraint would then have a slope of 1. And so Jack's indifference curve would be coincident with the budget constraint. So anything would be optimal bundle as Owen and Elodie, but wouldn't need to. Lastly, assuming Jack can raise his income without Owen's rising, what does Jack's income have to be able to purchase the amount of y bought by Owen? Well, remember, Jack has Cobb Douglas utility. So we want to know Owen purchased 60 units of good y. So how large does Jack's income have to be to purchase 60 units? Well, remember, with Cobb Douglas utility, you're going to spend a constant share of your income. So what must Jack's income be such that 60 is half of it? Oh, how do we know that? Because remember, Cobb Douglas demands are going to be alpha over alpha plus beta times m over py, or px, and then beta over alpha plus beta times m over py. So the ones that we're looking for, I'll try to get a text box so I can write that. And it made it there, and it made it here. Maybe some people haven't noticed that. I don't know. All right, so the demands for y star with Cobb Douglas is beta over alpha plus beta times m over py. Well, here alpha over alpha plus beta is 1 over 2, so it's 1/2. Income is 1, or let's just say m. And then what was py? Price of good y was 1. So we're looking for what, so we're given Jack's Cobb Douglas preferences, we're looking for what must Jack's income be such that 60 is half of it. That's where that was coming from. It's got to be Jack's earning an income of 120. And if so, If so, then Jack would be spending half of Jack's income on good Y, just as to consume the 60 units that Owen was, right? So this. Owen bought 60. Jack's expenditure on good Y is PY times Y is equal to 1/2, right? That's from this up here. Jack's expenditure must be half of his income on good Y. And then just solving. That's where that came from. So anyway, hope you enjoyed. Have a good night, everyone.